Females live at least a third of their lives in menopause. Unfortunately, menopausal women have an increased propensity to develop obesity-related diseases. Menopausal characteristics include loss of ovarian estradiol and can lead to physical inactivity, a shift in fat deposition to the visceral abdominal region, which is associated with insulin resistance and white adipose tissue inflammation, which increases disease risk. These characteristics are similarly seen in rodents following ovariectomy or ovary removal. Hormone replacement therapy has been shown to help reduce menopausal symptoms, yet there have been a multitude of issues associated with taking hormone replacement therapy. Therefore, more natural interventions are needed to reduce disease risks for this population. Exercise and a phytoestrogen diet have been suggested as interventions to improve menopausal symptoms in both women and rodents, but the mechanisms are currently unknown. The overall aim of my dissertation was to investigate the underlying mechanisms within the visceral white adipose tissue to determine how voluntary wheel running or a diet rich in phytoestrogens affects white adipose tissue health in ovariectomized rodents. My hypothesis was that voluntary wheel running and a diet rich in phytoestrogens can reduce visceral white adipose tissue inflammation associated with improved insulin sensitivity. My first aim focused on the exercise component, using rats with high intrinsic or low intrinsic aerobic fitness. In general, rats with high intrinsic aerobic fitness are protected against developing cardiovascular disease. They have better insulin sensitivity and lower white adipose tissue inflammation compared to low-fit female rats. Following ovariectomy, female high-fit rats still show improved insulin sensitivity and are protected against ovariectomy-induced increased adiposity compared to low-fit or more sedentary rats. Therefore, I wanted to examine whether access to a running wheel would reduce visceral white adipose tissue inflammation in the ovariectomized low-fit rats fed a high-fat diet. I found that access to a running wheel improved visceral white adipose tissue health by reducing white adipose tissue inflammation in ovariectomized low-fit rats despite a low volume of wheel running compared to the high-fit rats, and was associated with better insulin sensitivity. Thus, increasing physical activity can reduce white adipose tissue inflammation to reduce disease risk. A diet rich in phytoestrogens, or soy, was then examined using the OVX low-fit animals. So we asked the question, can a diet rich in phytoestrogens improve insulin sensitivity and reduce white adipose tissue inflammation in these rats? And we found that yes, it can. A diet high in phytoestrogens resulted in better insulin sensitivity and reduced visceral white adipose tissue inflammation in these low-fit animals. Therefore, for my dissertation, I wanted to delve into these mechanisms. Because phytoestrogens are estrogen mimetics and can bind to estrogen receptor alpha, the primary estrogen receptor, to induce estrogen signaling, it was logical to start with examination of estrogen receptor alpha to determine if the molecular mechanism by which soy improves metabolic and white adipose tissue health required estrogen receptor alpha. To address these mechanisms, middle-aged, approximately a year old, ovariectomized wild-type estrogen receptor alpha knockout and estrogen receptor beta knockout mice were used. A 3x2-way ANOVA, genotype by diet, was conducted and revealed no significant changes in body composition, white adipose tissue inflammation, or insulin sensitivity following this high phytoestrogen diet. However, there was a notable attenuation in final body weight, fat mass, and measures of insulin sensitivity in the estrogen receptor beta knockout mice, which only have estrogen receptor alphas. Soy also increased spontaneous physical activity in both the wild type and the beta knockout mice with preservation of lean mass, implicating that estrogen receptor alpha plays a critical role in maintaining systemic metabolic health following ovariectomy in these aged mice, and for the first time shows that estrogen receptor alpha, not estrogen receptor beta, mediates many of the protective metabolic effects of this high phytoestrogen diet following ovariectomy in rodents. Unfortunately, I did not see any changes in white adipose tissue inflammation following soy in these middle-aged mice. However, due to the initial increase in insulin sensitivity in the estrogen receptor beta knockout mice following this high phytoestrogen diet, I wanted to further examine the adipocytes. I hypothesized that direct estradiol, or a phytoestrogen cocktail, on primary cultured adipocytes would enhance insulin signaling via phosphorylation of AKT. However, it appeared that insulin signaling within these adipocytes was independent of estrogen receptor alpha. In conclusion, my dissertation studies have confirmed that exercise and a diet rich in phytoestrogens are two strategies that can effectively improve white adipose tissue health or insulin sensitivity during estrogen deficiency, partially by signaling through estrogen receptor alpha. Thank you.